Another parameter that affect the work of an axial compressor is stage loading. So we can translate stage loading as a ratio between the power input, or W, to the functions of mass flow rate multiplied with the square of the blade speed, or U to the power of 2. And this is a dimensionless parameter, and it has a symbol of psi. And as we know, we can write down this as functions of mathematically W divided with mass flow rate and square of U, or as we know previously, power input divided by mass flow rate is also equal to the total enthalpy rise across the stage, and the square of U is remain the same. And we have another way to note down the stage loading as a function of lambda. Lambda is another dimensionless parameter that known as the work done factor, and it is a ratio between actual work absorbing capacity and the ideal work absorbing capacity. So this work done factor is actually to compensate when CA is actually not constant across the axial compressors. So, but to simplify it, we normally count that CA is constant, but to count the effect that they are not constant, we use the work done factor, or lambda. And psi, or the stage loading, is functions of lambda multiplied with the difference between the Cx2 and Cx1 and divided by U. Or another way to represent the stage loading is by counting the effect of the absolute flow angle, or alpha, between the outlet and the inlet of the rotor, and the ratio between the axial velocity and the blade speed, or the ratio between axial velocity and blade speed, we can write them as phi, another Greek letter here. Now let's talk about the lift and drag coefficients of an axial compressors. Now we look at the axial compressors as an element of a blade, or this is, we know them normally as airfoil profile. This is, let's see them as a cross sections of, when we cut a blade of an axial compressor, it will look identical to this airfoil profile. And we have the relative velocity factor of W1 here at the inlet of the rotor and W2 at the outlet of the rotor. And they have the angle of beta 1 and beta 2 between the inlet and the outlet. As we know from the basic fluid mechanics on the chapter of external flow, then the lift and drag will develop across this airfoil profile due to the interactions between fluids and this solid surface. And to know about the lift and drag itself, let's assume that the drag force acts on the mean velocity factor of W infinite here, and at the angle of beta infinite, and this line is to the actual directions of the flow, and this is the same angle when we talk on the previous slides about the reaction ratio, the beta infinite. And as we know, we can write down the lift coefficients, or CL, as a functions of lift force divided by 0.5 multiplied with density, the relative velocity, or we know them as the mean relative velocity, multiply with the A, or the span-wise area of the airfoil. And A, or the blade area, is the product of chord, or we know them as C. We will use C later on this, and span, or small l, of the airfoil. And we can combine the lift and drag coefficients with the blade loading factor, or blade loading, that we just previously learned, and we can write them down as the blade loading factor, or psi, and phi multiply with ratio of C and S. C is the chord and S itself is the gap width of one blade passage, and multiply with the second of beta infinite, multiply with lift coefficients plus the drag coefficients, multiply with the tangent of beta infinite divided by 2. And to get the maximum efficiency, the mean flow angle, or beta infinite, is normally at the range of 45 degrees. And we can put them down and substitute the tangent beta infinite to tangent of 45, and we put it into these equations, and we get the optimum blade loading factor as phi divided by the square root of 2, multiply with the ratio between C and S, multiply with the combinations of lift coefficients plus drag coefficient. And in most cases, we found that the drag coefficient is normally smaller compared to the lift coefficient, so we can further simplify the equations for the optimum blade loading factor as the ratio between phi, or divided by the square root of 2, multiply with the ratio between C to S, multiply with the lift coefficients. And to recall your memory, phi is a ratio between CA and U, and this is the equations that we can use to get the optimum blade loading coefficients according to the lift coefficients. After looking at the lift and drag coefficients across an axial compressors, now we will have a look at the blade efficiencies and stage efficiencies. Now let's see that the blade draw efficiency can be defined, or can be translated as the ratio between the actual pressure rise in the compressor blade row to the theoretical pressure rise in the blade row. So this is on how we define the blade draw efficiency. So this is between actual and theoretical. So theoretically, the pressure rise across the blade row can be written as a functions of density, axial velocity, the square of tangent of flow angle at the inlet of the rotor, minus to the square of tangent of alpha 2 at the outlet of the rotor, divided by 2. On the other hand, the blade efficiencies, or this is a functions of the delta V theoretical minus to P0 divided by the delta V theoretical, or we can write them down as 1 minus 2 P0 divided by delta V theoretical. So V0 is actually the increase in total pressure between 0.1 and 0.2, and we take the absolute value of them, so there will be no minus on P0. This, and divided by the delta V theoretical or the theoretical pressure rise. So that's for the blade efficiencies. And also we have the stage isentropic efficiencies, that is the functions of temperature, and it is T temperature at the outlet of the stator at the end of pressure line 3 minus to the temperature at the inlet divided by the total temperature, static temperature at the outlet of the stator minus to the inlet temperature of the rotor. Or we can write them down as the functions of reaction ratio, or R. So these two, we can write them down as a functions of temperature or reaction ratio. And we can write them down as functions of reaction ratio and the blade efficiencies of the rotor for the stage efficiency. So this is already covered the stator and rotor, and this one it's only for the rotor part.